Good morning, ladies. This morning we are starting our new section, two-dimensional and three-dimensional wavefronts. Firstly, what is a wavefront? And according to our definition from the guidelines, it's an imaginary line joining points on a wave that are in phase, and we'll take a look at that in a little bit more detail a bit later on. Then just a bit of revision from work you did last year. You learned that visible light forms part of the electromagnetic spectrum. You also learned that light has a dual nature. It behaves as waves and it behaves as particles. Now, in this section, we are concentrating on the wave-like behavior of light. But before we look at that, we just need to talk about waves in a little bit more detail. Now, the principle of superposition, when two or more waves cross at a point at the same time, the resultant displacement of a particle at that point is the vector sum of the displacements resulting from the individual waves. You did this last year. It is worded a bit different, I know, but it's still the same thing. And then interference is the effect of superposition. Now this you also did last year, and I am sure you can still remember that we have got two types of interference. So over here we've got constructive interference. So I have two crests moving towards each other. This is where the constructive interference takes place. The two waves strengthen each other and they form a wave with a greater amplitude. So if the amplitude there was 5 centimeters and here it was 10 centimeters, here it is going to be 15 centimeters. And then very important, after the interference takes place over here, the waves move as before. So B is still moving to the left, A is still moving to the right with the original amplitudes that it had over there. Then destructive interference. So now I've got a crest and a trough moving towards each other. They are going to cancel each other out, and that is what happens over there. So if this was an amplitude of 5 and this was an amplitude of 10, this amplitude here would be 5 centimeters. And just like before, after the interference takes place over here, they move as before. And then just another example of destructive interference. This is when the two waves have got exactly the same amplitude. So I've got a crest and a trough that meet. They cancel each other out fully. So this is where your destructive interference takes place. And we say that a nodal line forms over there. And then just like before, after interference, they move as before. So this wave is still moving to the left, that one is still moving to the right. Okay, that brings us to experiment 6.1. This is on page 123 of your textbook. And this is actually something that you can go try at home. If you've got a container, a square container, and you fill it with a bit of water, and you take your two fingers and you touch the surface of the water like this, wave patterns will spread out from where you do this. And if we just look at this very quickly, you'll find that it looks something like this. So this is the pattern that forms. So what you must be able to do is explain what is happening there, and we can actually explain it in terms of constructive and destructive interference. So that is what I have tried to do over here. So what I've done is I've used different colors. So the black line represents a crest that forms from this source and a crest that forms from this source, and the purple lines represent the troughs. So from this source, I've got a crest, a trough, a crest, a trough, and so on. And then the same thing happens over here. So here, for example, you can see two black lines meet. So it's a crest from this source and a crest from this source. So what is that going to be? That is going to be constructive interference. Over here, for example, I've got two purple lines that meet. So a trough from this source meets a trough from this source. So what is that going to be? That is also going to be constructive interference. Where a purple, like over here, a purple and a black line meet, it means a crest from this source, a trough from this source. And what is that going to be? That is going to be destructive interference. So if we go back to the picture, we've got, it looks something like this. So that means there, for example, at there and there, that is where you have got your destructive interference that takes place. So those are actually nodal lines that form over there. And then this area over here and this area over here, as well as over there, that is where constructive interference takes place. So where there's a bright line, it's a crest and a crest that meet. A dark section is a trough and a trough that meet. And then a bright line, again, is a crest and a crest that meet. So this is why this area here, as well as there, is where constructive interference takes place. Right. Then, this is also something that you can go do at home. If you take a little block or something like that and you place it in your container with water, and you take a ruler and you strike the water surface like this continuously, you've got horizontal waves that form and that spread out towards the barrier. And then you should notice something very interesting. The waves actually bend around the corner or the edge of the barrier into the area behind the barrier. And this is what we refer to as diffraction. So diffraction is the ability of a wave to spread out in wavefronts as the wave passes through a small aperture, a small opening in other words, or around a sharp edge, as we saw over there. To explain diffraction, we make use of something called Huygens Principle. Every point on a wavefront serves as a point source of spherical secondary waves that move forward with the same speed as the wave. And that is what I try to do over here. So here are my horizontal waves that form. Now, according to Huygens Principle, if I take that horizontal line, like the one that I drew there, each and every point on that wave is a source of secondary spherical waves. But instead of drawing in for every point the waves that form, I've just chosen a couple. So I've said, let's look at this point, let's look at this point, and so on. So each point is a source of spherical waves. So those are the spherical waves that I've drawn in here in red. If I now take my pen and I connect the points in phase, so I connect this crest with this crest with this crest with this crest, and I do that, that is my wavefront, and that is where the next wavefront is going to form. And then the same thing happens. Each point on that wavefront is a source of spherical waves, and if I connect the crests of those spherical waves, that is where the next wavefront is going to form. So if you use that principle, you can actually see that here's a point, here's the spherical wave, there's the next wavefront that forms, and then each point on that wavefront is a source of spherical waves, and you can see that is the reason why it actually starts bending around the edge of the barrier that is placed in the path. Okay, lastly, the degree of diffraction or bending is influenced by two things: the wavelength of the waves and the width of the slit. So first, the wavelength. So take a look over here. So here I've got waves with a longer wavelength, and here I've got waves with a shorter wavelength. And with the longer wavelength, more diffraction takes place compared to the shorter wavelength. So our conclusion there will be that the degree of diffraction is directly proportional to wavelength. So longer wavelength, more diffraction. Shorter wavelength, less diffraction. And then if we look at the width of the slit, if I've got a smaller opening, more diffraction takes place. If I've got a larger opening, less diffraction takes place. And that means the relationship there is one of inverse proportion. So smaller opening, more diffraction. Larger opening, less diffraction. And then if I combine the two, it ends up looking like this. The degree of diffraction is directly proportional to wavelength and inversely proportional to the width of the slit or the size of the opening. Right, ladies, what you can do for me is exercise 6.1 on page 127. Use the colors like I did in my diagram. In other words, this one over here. Instead of using the colors as they've done in the textbook, I think this makes a little bit more sense. And then what we will do on Tuesday, I'll post the answers for you because Monday is a public holiday. And then on Tuesday, I'll also just post maybe a couple more of these pictures to try and illustrate the whole idea of diffraction when it comes to water waves in a little bit more detail. Right, thank you, ladies.